Welcome back to Examify's IGCSE Physics Revision Series. In this session, we will be focusing on Unit 5. This revision will guide you through the key exam-focused topics, including the nuclear model of atom, isotopes, Rutherford scattering experiment, nuclear fission and fusion, as well as the principles of radioactivity. Our goal is to make your revision clear, concise, and exam-ready, ensuring you understand the core definitions, processes, and applications that are most likely to appear in your exams. Let's begin our journey into atomic physics. Our first chapter for the day is the nuclear model of the atom. In this chapter, we will review the structure of the atom, isotopes, Rutherford alpha scattering experiment, and the processes of nuclear fission and fusion, including Einstein's principle of mass-energy equivalence. So let's go. Our first topic is the structure of the atom. An atom consists of a tiny, dense, positively charged nucleus surrounded by negatively charged electrons in orbit. The nucleus is made of protons and neutrons, together called as nucleons. The atomic number, also denoted by the letter Z, is the number of protons. The mass number, A, is the total number of protons and neutrons, and the number of the neutrons is given by A minus Z. Atoms are mostly empty space. The nucleus is about 1/10,000th the size of the atom, but it contains almost all the mass. Atoms can lose or gain electrons to form ions. Losing electrons makes a positive ion. Gaining electrons makes a negative ion. Next, let us revise the nuclide notation, a simple but powerful way to represent any nuclei. In nuclear physics, we represent isotopes using the notation A over Z followed by the element symbol. The mass number A is written as a superscript on the top left. It represents the total number of protons and neutrons in the nucleus. The proton number, Z, is written as a subscript on the bottom left. It represents the number of protons in the nucleus, also known as the atomic number. The element symbol, such as H for hydrogen or C for carbon, is written on the right. And as we saw before, the number of neutrons can always be found by subtracting Z from A. Moving on, we are going to see isotopes. Isotopes are atoms of the same element with the same number of protons but different number of neutrons. For example, carbon-12 and carbon-14 are isotopes of carbon. Both have 6 protons, but carbon-14 has 8 neutrons while carbon-12 has only 6. Isotopes have identical chemical properties, but their mass and stability differ. Some isotopes are unstable and thus become radioactive. And now we are going to see a very important experiment in the terms of atomic physics, the Rutherford's alpha scattering experiment. Rutherford's gold foil experiment provided evidence for the nuclear model of the atom. In this experiment, alpha particles were fired at a very thin gold foil, approximately 1 millimeter thin. The findings from this experiment are as follows. The first finding is that most of the alpha particles pass straight through the gold foil without any deflection. The conclusion from this is that atoms are mostly empty space. The next finding is a few alpha particles were deflected from the path but continued through the gold foil. This concluded that the nucleus of the atom has a strong positive charge. The last finding of this experiment is that a small number of alpha particles rebounded. The conclusion, therefore, is the atoms contain a small, heavy nucleus. If you are still struggling to identify these three findings, there's a 3D model in the next slide. You may refer to that for understanding better. The last topic for this chapter is the process of nuclear fission and fusion. Nuclear fission is the splitting of a large, unstable nucleus into two smaller nuclei, thereby releasing energy. It is used in nuclear reactors and atomic bombs. Nuclear fusion is the process of joining two light nuclei to form a heavier nucleus, thereby releasing energy. Fusion powers stars, but requires very high temperatures and pressures. In both fission and fusion, some mass is lost and converted into energy. This is explained by the Einstein's famous equation, E equals mc squared. A tiny amount of mass corresponds to a very large amount of energy. And this concludes chapter 20, the nuclear model of the atom. We revised the structure of atoms and ions, the role of isotopes, the experimental evidence for the nuclear model, and the fundamental processes of fission and fusion. Next, we will move on to chapter 21, radioactivity. Welcome to chapter 21, radioactivity. Here, we will focus on the nature of nuclear radiation, its detection and its properties, the effects of electric and magnetic fields over the radioactive elements, half-life, safety precautions, and the applications of radioactivity. First up, let's see how to detect and measure radiation. Radiation can be detected using a Geiger-Müller tube, or shortened called as GM tube, which clicks or counts when radiation enters. We measure the count rate in counts per second or counts per minute. However, the environment already contains background radiation from rocks, cosmic rays, and even natural isotopes in our bodies. In order to get accurate results of our radioactive isotope, we must subtract the background count from our measurements. Now, let us move on to some types of radiation. There are three main radiation types: alpha particles, beta particles, and gamma rays. Alpha particles can be described as a helium nuclei with a +2 charge and a relative mass of 4. They are heavy, strongly ionizing, but have a short range and can be easily stopped by paper. The next is the beta particles. They are fast-moving electrons with a -1 charge. They have moderate ionization, longer range in air, and are stopped by thin or thick aluminium. Last is the gamma rays. These are high-energy electromagnetic waves. They have low charge and very weak ionization, but very high penetration. Only thick lead or thick concrete can be able to stop them. Now we'll be moving on to an interesting topic in this chapter. This is the deflection of the alpha, beta or gamma particles in fields, either it be electric or magnetic. Because alpha and beta particles are charged, they are deflected by electric and magnetic fields. Alpha particles with a positive charge are deflected towards the negative plate. Beta particles with a negative charge are deflected towards the positive plate. This is because we know that unlike charges attract. Beta particles are deflected more strongly than alpha because they are much lighter. Gamma rays having no charge are not deflected. And now we will be moving on to the process of radioactive decay. This is a process where the nucleus of an unstable isotope emits radiation in order to become more stable, causing a change in the nucleus. For alpha decay, the nucleus loses 2 protons and 2 neutrons. It changes into a different element. For beta decay, nucleus loses 1 neutron and gains 1 proton, changes to a different element. This is because a neutron is classified as a combination of proton and electron. So when these 2 elements divide, the electron gets emitted as the beta particle and the proton stays in the nucleus. Lastly is the gamma decay. This is just a packet of energy being emitted. Since there is no change in the neutron or the proton number, it has no equation. As we saw previously about background radiation, it is the radiation that is present all around us in the environment, even in the absence of any radioactive sources. Some of the sources of background radiation are radon gas in the air, rocks and buildings, food and drink, and cosmic rays. Radiation is measured using a detector connected to a counter, which gives us the readings in pounds per second or pounds per minute. And we know that calculating the corrected count rate of a radioactive source is equal to the detector reading minus the background reading. Having learned about the different types of radiation, we need to know that these radiation may be harmful because it has the power to ionize the living tissue, leading to cancer or mutations. Some of the safety rules here include limiting exposure time, keeping distance from the source using tongs or remote handling, using shielding such as lead or concrete, storing the sources in lead-lined containers clearly labeled with hazard symbols. These precautions keep exposure as low as possible. A very important concept to note about radioactive decay, it is that it is random and spontaneous. Random as in, we don't know which atom or which nuclei will decay first. And spontaneous means that it is not affected by any external factors such as temperature, wind, pressure, etc. Now, for the half-life. The half-life of a radioactive isotope is the time taken for half of the nuclei in a sample to decay. For example, if we start with 1000 atoms, after one half-life, 500 remain undecayed, and after the next half-life, 250 remain, and so on. On a graph of activity against time, the curve falls by half in equal time intervals, showing the exponential decay. Last but not the least, we have some applications of radioactivity that we should remember. Radioactivity has many useful applications. Some of them are included in this chapter. In smoke detectors, alpha particles from americium-241 ionizes the air. Smoke interrupts the ionization as sounding the alarm. In medicine, gamma emitters like technetium-99m are used as tracers, and cobalt-60 is used in radiotherapy to treat the cancer. In industry, B-type sources monitor the thickness of materials like paper or metal sheets. Gamma rays are used to sterilize medical equipment and preserve food. Carbon-14 dating allows archaeologists to estimate the age of ancient objects. Well done! You have just completed Unit 5, Atomic Physics, with the Examify revision series. We revised the structure of the atom, evidence from the alpha scattering experiment, nuclear reactions, and mass energy equivalence, along with the essential principles of radioactivity, including radiation types, detection of radioactivity, half-life, safety precautions, and some real-world applications. Remember, strong preparation is about understanding the concept, not just memorizing them. Revisit this session as often as needed and use it to strengthen your confidence before your exams. Thank you for learning with Examify.